Welcome to week 4 for hematology. We are going to jump into it. We have 3 PowerPoints to go over today, chapters 10, 11, and 14. So I'm going to go ahead and share my screen so we can get going. All right. So we'll start with chapter 10, which is all about hemoglobin metabolism. So last week we learned our different cells that are involved in the cell line and getting to a mature red blood cell. Now we're going to learn about hemoglobin inside that blood cell. So a hemoglobin is a protein, and it consists of 4 heme groups and 4 polypeptide chains. You'll see that they're written as 2 pairs. So they occur in pairs. There's 4 overall, but they occur in 2 pairs. The actual heme group itself, not the hemoglobin molecule as a whole, but just the heme groups, those 4 heme groups, are made of carbon, hydrogen, and nitrogen atoms in a protoporphyrin ring. So when you look at that picture right there with the heme group, that is showing, all right, sorry about that, I've just got to reshare my screen. Okay, so as I was saying, that heme group inside the hemoglobin molecule consists of carbon, hydrogen, and nitrogen atoms, and we called it a protoporphyrin ring. So what you see in this picture is the protoporphyrin ring itself that is found inside a hemoglobin protein. So you can see the carbon, the hydrogen, and the ends for the nitrogen atoms all here. So inside the center of that protoporphyrin ring is our iron. Fe stands for iron. So it is in what we call a 2+ ferrous state. We must have iron in that 2+ ferrous state as part of this in order to properly bind to oxygen and deliver the oxygen. So this whole thing together, this ring plus the iron, make up each heme group. So there are 4 of them total. So where the oxygen binds with the hemoglobin is actually to the heme. So we've always talked about red blood cells deliver oxygen. Well, that oxygen is actually binding to the heme inside the hemoglobin. And the heme group, this protoporphyrin ring, is actually what will give your blood the red color that it has. So at some point when you guys get into clinical chemistry, if you're not there yet, there's a disease in clinical chemistry that's discussed called porphyrias. And porphyrias are diseases of this protoporphyrin ring. They might be missing a step in making this ring. There's a whole series of steps to make this ring. Now, we don't go into depth on that because I just keep it light for the view of our MLT hematology world. But when you get there, you'll learn that different enzymes can be missing, resulting in any various porphyrias. So that word for diseases comes right out of the protoporphyrin ring. That's that whole disease system, why they originally thought there was like the whole vampire mythology and all that. So if you're in clinical chemistry at some point, you might learn that. So it kind of connects here. But for our purposes, this is that protoporphyrin ring, and this is what gives blood the red color. All right, besides the heme group, there are also 2 pairs of what we call polypeptide globin chains. These chains are made up of sequenced amino acids. So these acids are sequenced together, and each chain is designated by a Greek letter. So we are going to have alpha chains, beta chains, gamma chains, and so on. So that is going to be assigned, and there will be 2 pairs of each one of those. So a lot of people might have 2 alpha and 2 beta in a hemoglobin. And of course, because hemoglobin is a protein, proteins are made of amino acid sequences. So here's where our amino acids are found. So overall, the entire hemoglobin structure kind of goes through 4 steps, if you will. There's the primary structure to the hemoglobin molecule, which is just referring to those amino acids sequenced together in the polypeptide chains. The secondary structure is going to have those chains arranging themselves into helices and non-helices. The tertiary structure is when they actually will fold into more of a 3D-like structure, and the quaternary is actually the entire hemoglobin molecule itself together. So when you put the whole thing together, it is spherical in shape, and you'll see it kind of represented by that diagram there in the picture. Again, 4 heme groups. Each one of those heme groups has an iron inside that protoporphyrin ring. And again, each one of these heme groups will bind an oxygen. So you can see an oxygen on each one of these heme groups. There are also 4 globin chains here. So you're going to have 2 alpha chains. There's always going to be 2 alpha and then 2 something else. It could be beta, it could be gamma, it could be delta, but there will be something else. There's always 2 alpha. And so again, 4 of each all together to make a hemoglobin. So if I were to ask you how many oxygen can one heme group carry, that's 1 oxygen. If I were to ask you how much oxygen can an entire hemoglobin carry, that's 4. Because there are 4 heme groups in a hemoglobin and each carry an oxygen, your hemoglobin molecule can carry 4 oxygen. So where in the red blood cell precursor does heme get made? So inside our bone marrow, we've learned we have pronormoblasts, basophilic normoblasts, polychromatic, and so on. Inside those red cells, they are actively making heme. So that way, when it gets to the mature red cell, you have heme in there carrying oxygen to your tissues. So inside those cells, we are making the heme inside the mitochondria. So in the pronormoblast down through even the reticulocyte stage, it is making heme in the mitochondria. Once it gets to the mature red cell stage, it can't make heme anymore because there are no more mitochondria. They're not there anymore. For the iron, we have to get iron inside that heme group. We're actually going to get iron through our diet from our food intake. And we have a protein that is called transferrin that will bring the iron to the red cell in the bone marrow to put it in. So the word itself for the protein, trans for transport, ferrin for iron, tells you that's its job. It's to carry iron. So when it actually does this, it brings it in the ferric 3+ form to our cells. Once it gets to those red blood cells, it will change into that ferrous 2+ state to go inside that protoporphyrin ring. Because again, in order to bind and deliver oxygen, it has to be in that 2+ state. While it's in transport, it stays in that 3+, but it will turn into the 2+ for the red cell. Once that iron joins up with that heme protoporphyrin ring, that will leave the mitochondria and go to the cytoplasm. In the cytoplasm, in the ribosomes of the cytoplasm, down here at the very bottom step it says ribosomes, that is actually where we're making our globin chains, because again, ribosomes make protein. This is a protein. So that's where all the amino acids are being sequenced together, put together, and making those globin chains. So once that's done being made in the ribosomes, that will go into the cytoplasm, and then that's when the heme and globin chains join together to make the hemoglobin. All right, so that's what it just kind of discusses here. Again, there's always going to be 2 alpha chains and then 2 other types of chains in that hemoglobin. So again, 4 heme, 4 chains all together. Now, in an adult, you have 3 main types of hemoglobin molecules, and these are the 3 types. So everybody has hemoglobin A. Well, that's everyone that's healthy, I should say. But the majority of our hemoglobin as an adult is hemoglobin A. Like 95% of our hemoglobin is hemoglobin A. And hemoglobin A is 2 alpha chains, 2 beta chains. So I would remember that. We have around 2 to 3% hemoglobin A2. That is 2 alpha, 2 delta chains. And then we have like less than 2% hemoglobin F. And that is 2 alpha, 2 gamma. Hemoglobin F is actually the one that's predominant in the fetus, F for fetus, if you think of it that way. And then when you're born, we don't have very much of it anymore. We have mostly A. So there is a chart, or this used to be in your book. I don't know. It might be in the new edition. I'm not sure. I haven't looked to see if it's in the new edition. But you have it here at Anywell. And you can see all the different types of hemoglobin that occur from the time you first start making that fetus, back in the yolk sac phase of that fetus, down through adulthood. What I need you to remember is for sure the adulthood. So you have your F, your A2, and your normal A. And there's the percentages that we have, like I said. And then you can tell which hemoglobin chains are involved. If you don't know your Greek letters, I would get to know these ones at least, knowing that that fishy thing is an A for alpha, you got the Y as a gamma, this little thing with a whoop is a delta, and then your B for beta. I know, great descriptions, I know. But anyway, this is the line you definitely need to know the adulthood. But it's kind of nicer to see what actually is involved in the other stages of your life. It's kind of a nice little reference point. Like I said, when you're first born and while you're a fetus, F is the primary one at that time. All right, just like anything else in your body, there's regulation to all steps of synthesis. Anything that's going to get made and done in a pathway is always regulated by your body. I don't test you on this regulation. This is just informational on how we're regulating that whole process. But again, what really regulates the process and what you need is your tissue oxygen, your hypoxia. If you have hypoxia or not, meaning are you getting low in oxygen? Do we need to kick up our hemoglobin synthesis process or not? Reference ranges, you can find these on that handout, that attachment that I had emailed out earlier, but roughly men are around 14 to 18, women 12 to 15. Newborns, when they're first born, they have a very high level of hemoglobin. That will go down as they get older. And then children have various amounts, but definitely know the men and the women reference ranges. Again, the function of hemoglobin, of course, is to transport oxygen. There is an actual curve that we call the oxygen dissociation curve to kind of help understand what's going on with our oxygen carrying and delivering ability. So this curve will differ depending on what's happening to that body. So we have what we call a Bohr effect, which has pH affecting that curve right here. So that kind of just talks about how pH of the blood can affect your hemoglobin or oxygen dissociation curve. If your pH gets too acidic, too alkaline, that will definitely affect it. You can read through this. I know that I don't typically read through things, but what I want, hold on one second. Yeah. What I want to do here first is just before we get into the factors that affect it, let's first talk about the curve. The curve will have a standard set way of it. If anything were to shift it, we call it a shift to the left or shift to the right. And that will affect what we're doing with the oxygen. So first you should know if your oxygen dissociation curve shifts to the left, that is going to indicate you have a very high affinity for that oxygen, meaning your hemoglobin loves it. I always think left loves. It really likes that oxygen, and it's not going to deliver it. It's not going to let it go. It's going to keep it bound to the hemoglobin molecule. So again, a shift to the left is always going to indicate a high affinity, a really liking. So it's going to hang on to that oxygen and not deliver it. If your oxygen dissociation curve shifts to the right, it will readily get rid of it. I always think right release. It will easily just throw it out. It will unattach itself from it. So again, if it shifts to the right, you're going to readily release that oxygen. So let's go through the factors that can put your oxygen to the left or to the right. So first and foremost is temperature of the body. When you increase your temperature of the body, so if your body temp increases, that will break the bond between oxygen and hemoglobin. As a result of easily breaking that bond, it shifts it to the right. It's releasing it easily. So a high temperature will shift it to the right, causing an easy release. Whereas the vice versa is true. If you decrease a body temp, if somebody has really like hypothermia where they have really cold, that's going to be a shift to the left where they're hanging on to it too much. They can't break that bond. It's a left shift. For pH, when we have a decrease in pH, meaning we have acidity happening, that's a shift to the right. When we have a vice versa, an increase in pH, an alkaline pH, that's a shift to the left. And I'm going to put that into perspective right. Oh, I don't have it on here. Actually, let me add that on here real quick. I'm going to type on here. Thought I had that. Okay, let me zoom this in. So I am going to hang in there with me, guys, because I do need you. This is something that affects not only hematology but chemistry class as well. So I do need you to know this. Of course, now I'm wondering what I'm doing. Okay, it's not going to let me do what I want there. But anyway, All right, it's not even letting me type on that, so I'm going to bring this up here. All right, so CO2 will also affect your oxygen dissociation curve. So if you have lots of CO2, if your CO2 concentration is high in your body, that is going to shift your curve to the right. If you have low CO2 in your body, that will shift your curve to the left. So what that indicates is CO2 actually acts as an acid in your body. I'm going to write that, acts as an acid. So CO2 is acidic. So if you get a lot of CO2 in your body, you get a lot of acid built up in your body, of course, that's going to make your pH drop into an acid range. That's why both a high CO2 and a low pH shift it to the right. So the minute that you have a lot of CO2 happening, a lot of acid, you're going to drop your pH into an acidic area. So that will shift to the right. What that means is you have a ton of CO2 and you have very little oxygen then. You have to get the oxygen out there. So if you shift your curve to the right, the hemoglobin will get that oxygen released. So that's why your body will naturally do that, want to release more oxygen out there to get it out there, because we need to take down how much CO2 is out there. And so then the opposite is true. If you have low CO2, you have very little acid in your body, so your pH goes up. It goes up into an alkaline range. So then what your body does is say, hey, we need to build up a little bit more CO2 here. Let's hang on to our oxygen so we can build back up the CO2 level. So that's why I'll shift left for loves. So just kind of, if you can remember the reasoning behind why it's doing this, that helps with it. Okay, so now that I've said that, let me go back to this. This was the last slide I was just on here, was 2,3-BPG. So in the exam review, I covered this, but I'm going to cover it again here. 2,3-BPG is a substance that its whole job, its whole function, is to help oxygen get released off that molecule, off the hemoglobin molecule. So if that's its job, is to help release oxygen, of course, if you increase your 2,3-BPG levels, that will shift the curve to the right. It will release it more. If you decrease your 2,3-BPG levels, you're going to hang on to your oxygen. It'll shift it to the left. So now, putting all that into thought, here's kind of a chart to show you which direction everything heads. You can ignore the line that says oxygen. Of course, anytime, we're just going to get rid of that to make it easier. This affinity, this last row, tells you how much you like your oxygen. Remember, if you shift it to the left, you have a high affinity, meaning you love it, left loves. And if you shift to the right, you have a low affinity for the oxygen, meaning right release. You want to get rid of the oxygen. So you do need to remember what each one of these will do. Okay, so I can now, now I can add in my CO2. So again, like I had said down here in the notes, a CO2 shift to the left is going to be low, a shift to the right is high. All right, if you actually look at this, if you notice, so now that you see all that, let me take out this row real quick for you. I know, I'll bring it back in. When you look at this, the arrows on here will go the same direction except the pH arrows. That's the only one that differs. When you look at the shift to the left, the pH will go high, but everything else goes low to shift it to the left. If you look at the shift to the right, the pH will go low, but everything else increases. If that helps you to remember it, so be it. You have to remember these results. And again, I know it's initially confusing at first because it's quite the topic. What you just have to remember is this whole oxygen dissociation curve is saying, if these things are happening in your body, one of these things are happening, your curve will shift one way or the other. And it tells us what's happening with your hemoglobin and oxygen bond. So again, if your body temp changes, your pH changes, if you're increasing or decreasing your 2,3-BPG, if your CO2 is increased or decreased, any one of these will either cause the oxygen to be hung on to more or cause it to be released more. So that's what we just went through. So again, temperature, the higher the body temp, the more it's going to break the bond. pH, the more acidic it gets, the more it breaks that bond. CO2, again, the more CO2 you have, you want more oxygen out there, so that'll break the bond. And 2,3 BPG, the more of that you have, the more it helps the oxygen get released. So if this takes you a while, just go back through it, re-listen to the recording, listen to the reasoning behind it. Now that I've kind of introduced the topic, it takes a minute for some of it to sink in for people. It gets a little confusing at first, but stop, re-listen to it, and hopefully it will start to make sense. But you do have to know each one of these and what it does to that oxygen dissociation curve. All right, so now with that being said, let's keep going. Now that we've discussed kind of our hemoglobin in general, there are some chemically modified hemoglobins. These are things that are not normal to have. These are things that something in your body has happened to result in one of these hemoglobin molecules. The first one that we have up is methemoglobin. Methemoglobin is when your iron is in the ferric 3+ state. Remember, when we first talked about heme being formed, we said that iron has to be in that 2+ ferrous state in order to bind oxygen and deliver the oxygen. If your iron goes into this ferric 3+ state, it forms what we call methemoglobin. That will basically mean it will continue to hang on to your oxygen and it will not deliver it. As a result, you'll get hypoxia, cyanosis, and your tissues will start to die because you're not delivering oxygen the way you're supposed to. It's hanging on to it for way too long. So that's the problem with methemoglobin and having iron in that ferric 3+ state. So the way that I always remember this is iron is supposed to be in the 2+ ferrous state, ferrous for us. When it's in a 3+ ferric state, it's icky, ferric icky. So you want it in the 2+ ferrous for us state. Sulfhemoglobin is different drugs and chemicals that you're taking can result in forming sulfhemoglobin. This basically just won't transfer oxygen at all. It just won't even bind it. It doesn't want anything to do with the oxygen. It won't pick it up. It won't bring it to the tissues. It won't even bind the oxygen. And then finally, the one that you probably have heard of a little bit maybe is carboxyhemoglobin. And this is when carbon monoxide poisoning happens. So we've heard about carbon monoxide poisoning can be very deadly when they've been exposed to it too long. And the reason it's deadly is that when you're exposed to carbon monoxide, CO is carbon monoxide, and your hemoglobin has a choice between oxygen and carbon monoxide, it picks the carbon monoxide every time. It loves itself some carbon monoxide. So your hemoglobin will bind up all this carbon monoxide and doesn't bind any oxygen. So then your tissues are not getting any oxygen and they're going to die, and that's what is fatal to that person. So your hemoglobin actually has a 200 times more affinity, more liking for carbon monoxide than oxygen. It kind of sucks like that. So that's what forms carboxyhemoglobin, is when it's hemoglobin plus carbon monoxide bound together. And it makes this really bright cherry red colored blood. It's kind of a classic color to it. So to measure hemoglobin in the lab, there is a reference method called the cyan-met hemoglobin method. This is kind of an older school methodology that was done on spectrophotometers, but many of your analyzers might be still using this technology inside the actual analyzer. But there is a way that we can even do this method on our basic spectrophotometers that we have in chemistry. So you do need to know this method, this measurement process, so let's go through it. So first what we do is we will take the patient's sample and we're going to add a lysing agent to that sample. And the lysing agent does exactly what it's called. It lyses the red cells. It breaks down those red cells so that we can get the hemoglobin out of the red cells. Because in order to measure anyone's hemoglobin level, we got to get them out of the red cells first. So that lysing agent will purposely lyse open the red cells to free the hemoglobin. Then we add a potassium ferrocyanide reagent next with that hemoglobin. When we add that, it will purposefully change the iron in the hemoglobin from a ferrous 2+ to a ferric 3+ state and make methemoglobin. So we're doing that on purpose with this reagent. We're using that potassium ferrocyanide to purposely put the iron in the 3+ state to make methemoglobin. And then we take the methemoglobin and combine it with potassium cyanide, and that's going to form cyan methemoglobin, which actually can be a color change. Cyan I think cyan is a blue color. I could be wrong now. But anyway, it makes a color change, and of course, spectrophotometers read color change based on wavelengths. So that's how we can measure hemoglobin. So I would know those basic steps for this methodology. Okay, so that was a big chapter. Let's go to our next PowerPoint, which is iron metabolism. I'm going to say this is much simpler than that last chapter. So this is all about that iron molecule inside the hemoglobin. All right, so overall in your body, 1/4 of your iron at any point in time is stored. And so that is stored either as ferritin or hemosiderin. Both are formed storage of iron. And then a little bit of your iron at any point is also bound to that transferrin protein being transported somewhere in the body. So through your diet, we are taking in iron, absorbing it. We're taking in about 10 to 20 milligrams of iron per day, but we're actually only absorbing 1 to 2 milligrams. And we can either absorb it in two forms, in the form of meat sources, so blood from the meat, or, of course, through non-meat sources like different vegetables and things like that. That's probably where majority of your iron is coming in, through the vegetables. By the way, this was all informational. I don't need you to remember that. And then for the absorption and excretion, lots of little processes here. This is, again, informational. But anything that we don't need at that current time that's extra, we're going to store it, again, as ferritin and hemosiderin. We can, of course, regulate this whole process like everything else in our body. So anything we don't need that's not absorbed or stored, we're going to get rid of. We get rid of it through the stool, lactation, and menstruation. So there's just your overall iron cycle itself. Again, the whole purpose of why we're talking about iron right now is that once it gets to that bone marrow, it's put inside that protoporphyrin ring in the ferrous 2+ state. So here's just the stored form, ferritin, hemosiderin. Hemosiderin is technically like a degraded form of ferritin. Most of this is stored in the liver, the bone marrow, the spleen, but a lot of it's the liver. All right. So again, when iron is traveling to the bone marrow, it's traveling on that transferrin protein in the 3+ state, but once it gets to the bone marrow, it'll change to 2+. And the rest of this, I really don't need you to remember. You'll have talk on iron in chemistry as well, because that's where this is measured, is in chemistry. But we do measure serum iron to see what people's iron levels are in their serum as it's being bound and transported and stuff like that. We do measure that to help us indicate if somebody's getting iron deficient or not. So that serum iron test is run in clinical chemistry. There's also another test that we call TIBC, total iron binding capacity. This is the number of available sites on the transferrin protein. So we can also actually calculate this. You just calculate it by, well, actually we can measure this and use that measurement to calculate, the percent saturation. So iron divided by TIBC times 100. So these are going to become important when we get into our anemias. We will talk about iron studies, these serum iron, the TIBC in the anemia. So I do want you to hang on to this information because it does become important. And then, of course, we can measure somebody's ferritin. How much do they got stored? I mean, anytime somebody's becoming iron deficient, typically their ferritin is the first to go. We'll use up our storage before we use up anything else. We can measure somebody's transferrin protein levels to make sure they have enough transferrin protein. You can even measure the protoporphyrin production process, if you will. So all of this is assessment of iron stores, and that's it. So just know those tests at the end there, especially. And the other big thing to note would be the majority of iron in your body is actually found in your red blood cells, in the hemoglobin. There is a zillion red blood cells. In those red cells, there's hemoglobins, and every hemoglobin has iron. So that's where actually the majority of your iron is in your red cells, not stored. It's actually, they're floating around in your blood right now. So a little bit on iron. So that was a nice kind of briefer one. And then our last one is routine testing in hematology. I can't remember if this is still chapter 14 in your book. It might have changed chapter numbers, but this is the one that's all about calculations. So you're either going to love this or you're going to hate it if you hate math. All right, so there is a ton of calculations. You are going to have an assignment this week practicing some of these calculations. I would highly recommend, and actually you guys should be doing this anyway, every week you're supposed to be doing those lab review questions before you get to lab. That way you can correct them together and you have an idea of what you're discussing, what's going on. They allow you to dig into the textbook. Let me just say this. I'm not a big chapter reader. I don't like to read my chapters in my textbooks either. But when you do those review questions for the chapter, you pretty much read the dang chapter by the end of doing that whole assignment. So do your lab review questions. It's important. They're there for a reason. They're really good questions. I find that people that actually do them, get them done, bring them to class, and have them ready to go, understand what's going on better. They perform better in the class. They've kind of dug into the chapter. They know exactly where things are in that chapter without even having to sit down and actually just read the chapter. They already know. So we need you to do them. And there's going to be a great review question on this chapter right here that has lots of calculation practice problems, because that's the key to getting calculations down, is to practice them. So with that being said, let's jump into our different calculations. So first up is manual cell counts. This was basically what we did before there was automation, before there was analyzers. And we used to use hemacytometers. So hemacytometers are little counting chambers that you put on underneath a microscope. You look in these little squares and you count the cells, and you use a calculation to determine what somebody's white blood cell count was, what their red cell count was, what their platelet count was. So that is what manual cell counts were for, and they were using this hemacytometer. Now for normal blood, we use analyzers, but a lot of labs still use those hemacytometers for body fluids, such as cerebrospinal fluids. They actually still do that, especially if they're a smaller lab. You can find body fluid analyzers in the large labs, but not every lab will have a body fluid analyzer. It's just not cost efficient. So you will still see them pull out their hemacytometer for things like that. All right, so again, hemacytometer, just known as a counting chamber. So you guys are going to get to see this in labs, so you can see it with your own eyes, look at it under a microscope to understand what it looks like. But it essentially has two raised 3x3 squares, so it's kind of totaled 9 millimeters. Each square is going to be made up of smaller squares, and then some have smaller squares within the squares, that kind of deal. So I know that there's pictures online, or there's probably even a picture in your book of this. And then because we're using the sample wet, it's like a wet melt sample, not staining or anything on this. We're just putting the sample on and looking at it, so there's no staining. We do need a cover slip, so you're always going to cover slip it. And there is a standard depth between the cover slip to the counting square, and that standard depth is 0.1 millimeters. I say that because that's going to become important in the calculation, so you need to remember that the depth between the cover slip and counting square is standardized at 0.1 millimeters. All right, so then in order to have the sample loaded on into that hemacytometer, we use a lot of times what they call it unipet system. Basically, you have to dilute your sample. So you're always making a dilution first before you're placing it on the hemacytometer. And there's different dilution amounts that you can do. Your lab will have a procedure on which type of dilution that they want to do. So they have to dilute it, whether it's for white cells, platelets, or whatever. So here's the actual formula to actually calculate the manual cell count once you get done. So there's two different ways. They're the same formula. They're just written out two different ways. So memorize one of them. You have to know one of them. They will get you the same answer. So basically, it's going to be the number of cells that you counted times your dilution factor. Because we're diluting this, we got to consider our dilution factor, divided by the area. So the area is going to be the number of squares that you counted, times your depth. Remember what I said, there's a standard depth between the cover slip to the hemacytometer. So this would be 0.1. So your depth would always be 0.1. It would never vary. So that is your overall hemacytometer calculation. Now, you could remember the bottom one. The bottom one's a little bit simpler. Cells counted times dilution factor times 10. What they did here is they took the depth out of the bottom denominator and put it up in the numerator. When they did that, it automatically became 10 instead, and then divide by area. That one's a little simpler for people to remember, but just know one of them to be able to calculate these. All right, with that being said, going into white cell counts, a lot of times they use either a 1 to 20 dilution or a 1 to 100, just depends on the substance they're using. Then they will put it on under the 10x objective. They're going to count typically the 4 large corner squares, but again, your standard procedure should tell you what squares you need to count the white cells in, and you're counting on both sides. So there's 2 sides to the Hemacytometer. When you count both sides, you're writing them down as separate totals. So if on one side you counted 50, and on the other side you counted 60, you have to average those 2 sides before you put the cells counted number in here. You don't add them together, you're averaging. You want your 2 sides to be pretty similar. I mean, if you're counting 300 cells on one side and you only counted 20, you're not going to use those numbers. That's not okay. Like, that didn't make sense. But if you're getting 50 on one side and 60 on the other, those make sense. That's okay. Then you average that. All right, so that is a Hemacytometer calculation. It's the same thing for white count, red count, or platelet count. They just use a standard dilution, and then they'll use different cells or squares in there to count the cells. There's also what we call a corrected white count, and this we still do to this day. This has to be done even with our automated analyzers because actually of automated analyzers. So sometimes people have different diseases or conditions that will result in you seeing what we call nucleated red blood cells in their blood. All right, we just learned blood cells. We learned that there's a pronormoblast, basophilic normoblast, all the way down through ortho. All of those have nucleus to each one of them. Typically, they're only in the bone marrow. But sometimes people's different conditions, say like leukemias, will cause them to come over into the bloodstream where we might see them in the blood as well. So usually we're just seeing mature red cells and maybe some reticulocytes that don't have any nuclei. But if we do start to see the immature cells show up with the nucleus to them, we have to be careful because what your analyzer will do is they won't know that those are red cells. An analyzer is built to understand that a red blood cell has no nucleus. And so when this goes into the analyzer, it thinks it's a white blood cell because of that nucleus. And so it'll count all those nucleated red blood cells as white blood cells. And that will cause your white cell total to be falsely increased. So when we look at it under the microscope, if you're seeing a bunch of nucleated red blood cells under the microscope, right away, you're going to have to fix that white count because all of a sudden you know that analyzer counted them wrong. So most labs will have a standard rule. They'll say anytime you see 5 nucleated red cells or more, we have to correct the white count. So what you do is you take the original white count given to you by the analyzer, so what we call the uncorrected white count. So whatever the analyzer first gave you as a result, we take that number times 100 divided by the number of nucleated red cells we counted under the microscope plus 100. So it's a simple calculation, but it's important so that we can fix that white count number and get a more accurate result. So you will need to know that calculation as well. So let's practice that real quick. So if an analyzer told us the white count was 18.9, we looked at we did a manual differential under the microscope and we counted 18 nucleated red cells. So again, let's plug in the numbers. You plug in the 18.9 white count into the first, times that by 100, so do that separate. And then on the bottom side, you have the number of nucleated red cells, 18 plus 100, so that would be 118. Divide those two values, and in this case, you should get 16 as the corrected white count. So it is a difference between 16 to 18.9. As far as units, these times 10 to the 9th, it's going to be the same units as what was up in the white count number. So just put the same unit of measure there. All right. So again, like I said earlier, platelet count can be done on hemacytometers. They can use different dilutions, count different squares. Again, you're always averaging the 2 sides that you come up with. I discussed this a little bit in the exam review today because I think we've mentioned it elsewhere, but there are some platelet count errors that occur within an analyzer as well with what we call platelet satellitosis. So some people's blood will react with the EDTA anticoagulant, and their platelets will satellite or ring around those neutrophil cells. As a result, when you put that patient's blood through the analyzer, it thinks it's just one big cell. It doesn't count those platelets individually. So when you see this under the microscope, you've got to fix the problem. And what we do to correct it is we actually will take a sodium citrate light blue top tube, run the platelets count through the analyzer on that light blue sample, and then once we get the platelet count, multiply it by 1.1, and that's a true reflection of your platelet count. Again, you can do a red cell count on a hemacytometer. It's not done very often because, oh my God, there's a million red cells, so it's really hard to do. But it could be done if you wanted it to be done. All right, hemoglobin determination, we just discussed this. The classic methodology was that whole cyan-met hemoglobin measurement with a spectrophotometer, blah, blah, blah. So that whole thing is just rediscussed here. So we just went through that, so I'm not going to read through this slide. Once we have what we call the hemoglobin and the hematocrit results from the analyzer, we always do a rule of 3 check. So if you're that lab tech working hematology and you're getting results off the hematology analyzer, every time you get a result, you need to do a quick rule of 3 check. It's just a quality check to make sure that the results you're getting seem appropriate. So usually, if somebody has normal size cells for their red cells, so when I say normocytic, normochromic, I know those are not terms that we have learned yet. We're going to learn them. But that basically means that their red cells look normal and healthy. Their red cells are pretty good. Your hemoglobin value times 3 should be roughly your hematocrit value. So if somebody had a hemoglobin of 8, 8 times 3 means that their hematocrit should be roughly around 24. So with give or take 3, plus or minus 3. So it could be anywhere from 21 up to 27 would be an okay range. So that's just a quick check. So if I'm looking and I'm like, oh, this person has a hemoglobin of 8, should be roughly 24, give or take 3, and say it was 26, I'd be like, oh, we're good. It's good. It's a good quality check. We know that those results seem appropriate. So that is the rule of 3. Red blood cell indices are next. So we use the red count, the hemoglobin, and the hematocrit values all to help determine these red blood cell indices. These are going to become crucial when we get into the anemias. We talk a lot about these because we categorize our anemias according to these. So the 3 red blood cell indices are mean cell volume, MCV for short, mean cell hemoglobin, MCH, and mean cell hemoglobin concentration, MCHC. So these 3 values are going to help tell us how big our red cells are, if they're normal in size, and if they're normal in their hemoglobin amount inside of them. So again, it's just really going to help us tell apart our anemias and categorize our anemias down the road. So for the MCV, that is going to tell us the average size of our red blood cell. So the way you calculate it is you take your hematocrit times 10 and you divide that by your red blood cell count. So I have an example here. If your hematocrit was 45% and your red blood cell count was 5, you simply just do the 45 times 10 divided by 5. You do not have to change that percentage back to decimal form. So 45 times 10 divided by 5 would be 90, and the units are going to be femtoliters, FL. So that will tell you the size. Your MCH is mean cell hemoglobin. This is going to tell you the average weight of hemoglobin in your red cell. The units will be picograms, PG. So it's your hemoglobin times 10 divided by red count. So similar to the last one, just now we're using the hemoglobin because we're looking at the average weight of hemoglobin. So if your hemoglobin was 16, your red count again 5, it's just 16 times 10 divided by 5, should be 32 picograms in this case. And then your MCHC, this is looking for the hemoglobin concentration average in each red cell. So the units here are going to be grams per deciliter. You can also sometimes see the units as a percentage either way, but I always like to use the grams per deciliter units of measure. So the calculation is going to be hemoglobin times 100 divided by your hematocrit. So if, again, your hemoglobin is 16 and your hematocrit is 48, you go 16 times 100, divide by 48, and that will get you your MCHC. So now let's go over the reference ranges because we need to know those reference ranges as well. So for the MCV, again, MCV is telling us the size of our red cell. A normal size would be between 80 to 100 femtoliters. Anything in that range is a normal size red cell. And we would term that normocytic. So that is the term we would use to say, yes, these are normocytic, so meaning they are normal size red cells, especially when they're 80 to 100 femtoliters. If that result for the MCV was less than 80, was low, we would call that microcytic, micro for small. These would be small red cells. And then the opposite. If the MCV was high, higher than 100, it would be macrocytic, macro for large. For the MCH, the reference range is roughly 28 to 32 picograms. There's no terms to know here, so you just have to know the reference range and if it was in or not and how to calculate it. And then for the MCHC, the reference range for this is 32 to 36. If you were to have something within 32 to 36 for that MCHC, that is normal. So we would say that's normal chromic. So that's saying we have an average amount of hemoglobin concentration in our red cells, so normal chromic. If it is low, less than that 32, it's hypochromic, hypo for less. So it'd have less concentration, and then greater than 36 is a term that not everybody likes to use. Technically, you could say it's hyperchromic, but let's just put a warning on this. It should be very, very rare that you ever get an MCHC greater than 36. If you were to get that, you need to check that because either there's something wrong with the sample or they should have what we call spherocytes in that sample. We will talk more on spherocytes later, so don't worry about that, but just know, future warning, very rare to have over a 36 in real life. We might give you examples in class, but in real life, you wanted to check that out. That's not often. All right, so there's kind of a summary of those terms and the reference ranges a little bit there for you for the MCV and MCHC since they had terms that are involved. So now you can see we can put those terms all together to tell us how those red cells look. So if somebody's cells were described as normocytic, normochromic, we know that they're nice, healthy-looking cells. With reticulocyte count is something else that we often do in the lab, and this is to help kind of assess somebody's bone marrow erythropoiesis production rates. So we, like I've said before, everybody has reticulocytes in their bloodstream along with their mature red cells. Around 1 to 2% in your blood is reticulocytes. So of course we will find reticulocytes in the bone marrow and then 1 to 2% in your blood. If your reticulocyte count goes higher than that 1 to 2%, that is indicating that your bone marrow is really picking up production of cells and kicking out more and more. So that is why we use reticulocyte counts to help us assess the erythropoiesis, the red cell production in the bone marrow. Because anytime those reticulocytes are high, that's telling us our bone marrow has really picked up production and putting out a lot of red cells. So remember, reticulocytes are the stage right before a mature red cell. They still have that slightly blue-gray color because they have remnant RNA in them. So what we can do, and you guys will do this in lab, at some point this quarter we're going to do this in lab, but instead of using the normal white stain, we can actually use a supravital stain. So one of the supravital stains I think that we use in lab is new methylene blue. We can stain your sample with that new methylene blue, and that supravital stain is targeting that RNA left over in the reticulocytes. And so when you look at it under the microscope, those reticulocytes will look speckled because that RNA has really picked up inside there. And so we're counting the number of reticulocytes that we see in that smear. So we're counting a total of 1,000 red cells. So overall, you're going to count 1,000 red blood cells, which actually doesn't take that long as you think. And out of those 1,000 red cells, we're counting how many are actually reticulocytes. And so once we do that, we can calculate our percentage. So it would simply be the number of reticulocytes you counted divided by your 1,000 red cells times 100% to get your percent retic. So for example, if you had 15 reticulocytes, it would just be 15 divided by 1,000, and then you times it by 100%. So in this case, that'd be 1.5%, which is a normal value. We can also come up with the absolute reticulocyte count. The absolute is basically just giving us the actual number of retics. This last one was a percentage. Percentages are always estimations, whereas if we do an absolute count, it's giving us the real value of reticulocytes. So you just take that reticulocyte percentage, times it by the red cell count that you get from your analyzer, divided by 100. So in this case, if you had a 2% reticulocyte, you take that times the analyzer result of 2.2, and then divide by 100. Now, there is a trick to this, and this always gets people. If you notice, on my red cell count value, I had it in units of measure times 10 to the 12th. That's what you normally get. When an analyzer gives you a red cell count, it's usually in the units times 10 to the 12th per liter. Now, if you look down at my actual result, my result here is in times 10 to the 9th. So what you have to do, when you actually calculate this, do it right now. Take out your calculator, and you should plug this in because it'll help you understand. So plug in 2 times 2.2, and then divide that by 100, and you should get on your calculator 0.044. Now, I said 44. You see what I did? I moved that decimal over 3 spots. You have to do that to get it into the units times 10 to the 9th, because otherwise it's still in the times 10 to the 12th units. So on your absolute count, always move your decimal over 3 spots to get it in the right units for the absolute reticulocyte count. So if I move that over 3 spots, now I have my 44. And so the reference range is going to be 25 to 75, because that's in the times 10 to the 9th units. So 44 is nice and healthy right within that normal reference range. There is also a corrected reticulocyte count. When people have a super low hematocrit level, they will have a falsely increased percentage of reticulocytes. So if you're going to do a percentage of reticulocytes and you happen to notice that patient has a really low hematocrit, then you might need to do this corrected reticulocyte count. So it's your reticulocyte percentage that you came up with times the hematocrit that they have divided by 45. And 45 is just an average hematocrit level. That's why they use that number. And so that will give you the corrected retic count of what it really should be. And then there's what we call the reticulocyte production index. So this is basically your bone marrow response. So we have what we call shift reticulocytes, and I know this was a term that was on your red cell study guide. These are reticulocytes that are released even earlier from the bone marrow. Yes, we have retics in our blood, but there's a stage at which the retics can be released very early in their retic stage called a shift reticulocyte. We usually see this anytime that we're getting super low on oxygen, like in different anemias, and your bone marrow is trying to compensate and keep up with that anemia and get the oxygen out there. So as a result of these shift reticulocytes, they're really blue-gray in color, and that becomes obvious, and it's what we call polychromasia. Polychromasia is referring to when you have a bunch of blue-colored red cells on your peripheral blood smear. So that blue-gray coloring of the reticulocyte is really obvious, and we can call it polychromasia. So we can actually measure the reticulocyte production index of that bone marrow, how it's producing these reticulocytes and putting them out into the blood. So first and foremost, you have to use the patient's hematocrit value, and you're going to get what we call a correction factor, the number of days it takes to for them to mature, for these reticulocytes to mature. So if somebody's patient hematocrit value is 40 to 45%, it's a correction factor 1, and so on. Now, you're not going to have to memorize this. This is something I don't ask people to memorize. This is something that will be given to you. I just think we have enough to remember in the scope of everything. So if this were to be on a future test, I will try to make sure that your lab instructors give this to the proctors on campus so that you have access to this chart. So here's the actual calculation that you unfortunately do have to memorize. It's going to basically be your corrected retic calculation divided by the correction factor. So it's that retic percentage times your hematocrit divided by 45 and then divided by the correction factor. So you'll notice that there's brackets here around the hematocrit divided by 45. You have to do that first. That's the first step you should do in this calculation. Then you multiply it by the reticulocyte percentage, and then you divide that whole thing by the correction factor that you got out of this chart. So if this person had a retic count of 7.8%, a hematocrit 30%, they went to the chart, they found 30% was a correction factor of 2. We can plug those values in to the equation. Again, do the brackets first. So first we do 30 divided by 45, then multiply that by 7.8, and then divided by 2 to get your RPI, your reticulocyte production index, of 2.6. So as far as reference ranges go, anything above a 3 is saying your bone marrow is doing great. It is responding good to the anemia, it's compensating, it's doing its job. If it's less than 2, your bone marrow is not doing its job. It's an inadequate response. It's not putting out enough. Now, I have had people be like, well, what happens between 2 to 3? Well, it could go either way. It's kind of something you just kind of watch. Okay, that's always a long chapter. Oh, I'm exhausted just listening to myself talk, my God. So there will be an assignment to put to practice those equations. Make sure you do your lab review questions sheets that come out of the course. That will help you practice those, because that's the best way to learn these calculations is to practice them. You're going to have to memorize these for upcoming quizzes and tests. So if you guys have any questions, as always, make sure that you reach out. Otherwise, have a fabulous week, and thanks so much for listening.